So today's video is going to focus more on quantitative variables. So those variables that we can measure and the graphs that are associated with those kinds of variables. So first, let's look at the difference between a discrete versus a continuous variable. So a discrete variable can be calculated or counted in a finite amount of time, where a continuous variable cannot. So for example, a discrete variable could be the number of shoes in your closet. It could also be the number of shoes in the world. It could take us a really long time to count that, but I could still count it in a finite amount of time. A continuous variable may be, let's see, like height of everybody in the world, right? So height, I can take out to an infinite number of decimal places, right? So that's what a continuous variable is versus a discrete variable. Discrete variables have specific set values, where continuous variables basically cover every possible value in between. So let's look at our first one here. Let's look at a dot plot, which hopefully you're familiar with from math class, right? When we draw a dot plot, the first thing that we need to do is we need to get our x-axis happening, right? And anytime that we draw an x-axis, we need to label it and we need to put any units that are there. So for this particular problem, we are referring to the number of goals that were scored. So now that I've set up my x-axis, I need to set up a scale for my x-axis. My highest number here being 14, my lowest number being 0. So I'm probably just going to go by ones here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want to make this consistent as we move through. So I'm going to go ahead and label my x-axis there with my units with my consistent scale here. Okay, and then I'm just going to take and I'm going to mark one dot for each value at that location. So for instance, 1, and then 3, and then a second one, I just put it right on top of the first one. And then a 14, and a 13, and a 4, and another 3, and a second 4, 2, 5, a second 2, 0, a 4. And so as I'm doing this, I can start to see patterns developing, shapes developing. I could start to make some comparisons amongst these various values. I can get a feel of which ones are scored the most often, which values are scored the most often. I could calculate mean and spread and things like that. Okay, so that's how we would do a dot plot here. So once we've recorded our quantitative data, so for example, the example we just did with women's soccer, that was an example of quantitative data, right? We're counting the number of goals. Discrete data, I can't have 1.5555720 forever goals, right? I have 1, I have 2, I have 3. So we've graphed that data on our dot plot. We can then start to look at the distribution of that quantitative data. So for categorical data, we looked at like marginal distributions and we looked at conditional distributions. So for quantitative data, we're going to be looking for, like we did before, patterns and large things that depart from that particular pattern. And basically, when you are asked to describe a quantitative variable, you're going to want to address shape, center, and spread, as well as anything that would be considered possibly an outlier. So an outlier would be something that is kind of way out of the norm. The acronym that we use to help you remember this is that we cuss our quantitative graphs. We address the center, we address any unusual features, the shape, and the spread. So we will get more specific as we move through this, but center, for example, on our dot plot could have been the midpoint. As we move further in this, we'll talk about using mean versus median for our measurement of center. right? But basically where the data is clustering, the area the data is clustering around in the center. Okay? Unusual features would be things that really stand out, that are really separated from the other items. For instance, the fact that we had those 13 and 14 goals, you know, how we had 0, 1, 2, 3, and 4, and then nothing, and then 13 and 14. So 13 and 14 could be considered possible outliers. Later, we will have ways to calculate outliers. For now, we would say things like it's a possible outlier because we haven't calculated it yet. Okay, for shape, we're looking at things like how many peaks does it have? How many, like for instance, on that dot plot we just did, the overall shape is kind of like this, right? So we're looking for the main peak, if there is one peak. So for instance, this one had a peak at about 4. There was, you know, a large cluster of dots between 0 and 5. There was a large gap from, you know, 5 to 12. So all of those things would be part of the shape, as what it would tell us there. For spread, we could be looking at a variety of things. Again, we will calculate spread later using things like IQR and standard deviation. Again, we will calculate those things later. For right now, where we have no calculations, for instance here, our spread was 0 to 14. That's different than range. The range would just be one single number at 14. Okay, but our spread here is anything from our minimum, which was 0, to our maximum, which was 14. So this acronym is when you're describing your quantitative variables: center, unusual features, shape, and spread. So as in our previous video, pause for a second, read the problem so that you know what it's asking you, and you can go ahead and attempt it, and we'll talk about the solution. Okay, so as we look at this, let's remember again our acronym. We're going to cuss this graph. So if we look at the center first, the center, as we look at these, I can look at these and see that I have a midpoint around 28. Okay, so this would be about in the middle here. So a midpoint around 28. Okay, and so what that would mean would that we'd have a typical model year of 2012 mid-size car in the sample gets about 28 miles per gallon on the highway. That's using our context there. So again, when you're solving these problems, you're going to want to put your context in there. Somewhere in this CUS acronym, you needed to have addressed that you're talking about 2012 mid-size cars and how much gas mileage or miles per gallon they are getting on the highway to be able to receive full credit. Okay, so for our unusual features here, we've got 2 cars here that could be possible outliers that are getting very high amounts of gas, the Hyundai, and where is the other one? And the Toyota Prius. Okay, and then we've got our shape and our spread for our 2 S's. Okay, so for our shape here, we have a peak around 30. So I've got a peak around 30. Most of my data points are clustered between 24 and about, I don't know if that's 31 or 32. Okay, so, but most of my data points, you can even go all the way out to the 34 here, that most of your data points are clustered here between 23 and 34. You can adjust the gaps, the fact that you have some gaps between 34 and 40, between 40 and 48. All of those would contribute to the shape. And then for the spread, the data is going to vary from 18 to 48 miles per gallon. Again, context. I know you're not seeing me put a lot of context on these notes right now, but what that makes, it makes the screen very, very messy and it makes it hard to follow. So I cannot emphasize this context enough. So let's look a little bit closer at shape. So looking a little bit closer at shape, we can describe our shape as being roughly symmetric where the right and left sides are approximately mirror images of one another. We can also talk about skewing it to the right side versus skewing it to the left side. So if we look at, I apologize for all the bells. So we look at this first graph here and we kind of roughly draw over it. This first graph here is roughly symmetric. The right and left sides are approximate mirror images of one another. If we look at the second graph with B here, okay, our peak is kind of off to the side. And this one here, this one is actually considered left skewed, not right skewed. Some people get confused and they think it's right skewed because the dots here are on the right side of it, but it's really referring to which side is longer. This left side is much longer. So this would be an example of left skew, where this would be an example of right skew. Okay, so we have left versus right skew, where this is approximately or roughly symmetrical, where the two sides are mirror images. One of the ways that you can remember this is if you actually put your feet, if you imagine putting your feet or stepping on the graph, the big toe, which is normally taller than the rest of your foot, okay, this would be my left foot with my big toe there in the peak. And this one over here would be my right foot with, oh, that toe is struggling. This one here would be my right foot. So it is right skewed. Another way we could talk about shape is the number of peaks that that shape has. So in this graph here, for instance, as well as this one, those are what are called unimodal. They have one peak here. And so if I look at this example down here, I have two very distinct peaks here. And so this one would be considered bimodal, bi for two. In theory, you could have a multimodal, but we don't look at many of those. Okay? Most of what you guys are going to see in here is either going to have one peak, possibly two. Okay, so let's look at an example here where we're going to compare distributions from two different sets of data. So looking at this one here, how do the numbers of people living in households in the United Kingdom and South Africa compare? To help answer this question, we use Census at Schools random data selector to choose 50 students from each country. Figure 1.12 is a dot plot of the household sizes reported by the survey respondents. So one of the things that we need to realize is that when the question asks us to compare, we need to be sure that we are actually doing that. If you do not use comparative language, you will not get full credit. So you can't just describe the South Africa distribution and then describe the UK distribution. You need to specifically compare them to one another. The example on the right there is talking about using greater than or less than or about the same as. Okay, but you have to use that comparative language. So I've been asked to compare the distributions. So again, just like when I describe the distribution, I'm going to use my acronym. So I'm going to compare the two centers. So South African center seems to be greater than UK. Again, I am shortening this a lot for like messy standards on the screen here. Key thing that is missing there, right, is our data, is our context here. South African students, household sizes is our context, not just South Africa. What in South Africa are we talking about? We're talking about household sizes. So household sizes in South Africa tend to be larger than household sizes in the UK. And then we could put down the actual midpoints. The fact that the midpoint of South Africa is at approximately 6, where in the UK it's approximately 4. That would be a complete answer. What I wrote is not a complete answer. Okay, to see a complete answer, if you look at page 30 in your book, that kind of gives you a better understanding of the written out, exactly how much context is involved. You'll learn very quickly this is a writing class, not really a math class. Okay, so our U for our unusual features. Okay, so there do not appear to be any outliers in the UK. So no apparent outliers in the UK. And then for South Africa, there seems to be approximately 2. So there's 2 potential outliers here and here for South Africa at 15 and 26 people. Okay, for our shape and for our spread. So for our shape, okay, the shape for the UK sample. So UK is roughly symmetrical. So household size is roughly symmetrical and unimodal. So remember, unimodal is the one peak compared to, that's all you have to say, that be comparative language right there, compared to the South African one that appears, if we look at it and we've got this long tail, right? If I stepped on that, my right foot, the big toe would be there. So compared to the South African one that appears to be right skewed, but also unimodal, using that comparative language. And then for our spread, the household sizes for the South African one seems to vary more. That's comparative language, right? South African household size varies more than the UK household size. And then you can pull in your actual numbers, about 3 to 15 to 26 people. Okay, and then for the UK, approximately 2 to 6. So more variation within the South African, again, using that comparative language. Okay, so let's look at another type of graph that we can build with quantitative data. This is called a stem plot. Sometimes it is called a stem and leaf plot. To make a stem plot, you're going to divide all of your numbers into what's called the stem versus the leaf. The leaf is going to consist of the last digit only. So in this example here, it's talking about the number of pairs of shoes for the female students from their school with this data set here. So the leaf, for instance, would be 0, 6, 6. And our stem is going to be everything that's not the last digit. So the 5, 2, 2. Let's say I had a number of 1,123. Right? This is my stem. This is my leaf on the end here. So when I separate these out, I'm looking at my stem, and I'm going to go ahead and I'm going to put my stem down the middle. So 1, 2, 3, 4, 5. And then I'm going to put my leaves off to the right. And I'm going to ideally put those in ascending order. So I'm going to look at the ones first. So I have 13. So I have 3, 3, 3, and 5. So I have 3 threes and a 5. Okay, and I'm going to go ahead and, so I know I already did those. Right, so then I'm looking at my 2s. I have a 2, 2 3s, a 4, and 2 6s. So a 2, 2 3s, a 4, and 2 6s. So I got all my 20s out of the way here. And then for my 3s, again, I have a 0. I have a 1 and a 4 and an 8. Sorry, I almost missed that one. Okay. And then, I missed a 9 in the 1s. And then I jump up to the 5s. So I have 2 zeros. I have a 1 and I have a 7. Okay, so that would be my stem and leaf plot. Your stem and leaf plot also always needs a key. No key, no credit. So with a key, you're going to use an example from the stem and leaf plot. I missed the 9 there with the 4. So for example, 2, 2, and then I'm going to explain exactly what that means. So that represents a female student. So that represents a female student who reported or who said that they had 22 pairs of shoes. And so now that's, I know what my stem and leaf plot numbers represent. I can also adjust the scale of my stem and leaf plot. Let's say in the twos here, let's say I had like 20 pieces of data. Well, I could adjust my scale and I could break up the twos. So maybe this first row contained zeros and up through fives. And this second row could contain the rest of it. So that's just another, just want you to realize that you can kind of divide your scale up on your stem and leaf plots as well. Stem and leaf plots can also be set up in what's called a back-to-back stem plot. So this is the same data that we were just looking at. A number of shoes reported, females, males. You may have noticed on the previous slide that the male data was there. This one's been split up like we said. So it looks like 0 to 4 and then 5 to 9 is on the next line. So this one has been split up like this. It's got a key, and you'll notice they're what's considered back to back. So males are running in this direction, females are running in this direction. Okay, so that can allow you to compare these numbers amongst the two. So this question here is asking you to use the back-to-back stem plot, right, to compare the numbers of shoes owned by males and females. Again, remembering that we have to use that comparative language there. So if we look at this, let's talk about our center first, right, if we're comparing the two. So the midpoint for males and the number of shoes they own is less than females. The midpoint for males seems to be about here, so maybe about 9 pairs of shoes, where the midpoint for females seems to be higher, maybe in this area or so, about 26 pairs of shoes. So again, comparative language. Our our unusual features. So males have apparent outliers at 22, sorry, if I try to write fast, it's very messy. 35 and 38 for the males. Females, I would say they don't really appear to have any outliers or any apparent outliers. And then remember your shape and spread. So my shape for the males looks to be, so when you're doing shape for a stem plot, take it, rotate it 90 degrees down like this. So now I'm looking at a shape like that, right? So for males, it appears to be right skewed because that would be my right foot there, unimodal. Now for females, you can't just take the females and knock it down because that puts 0 on this side and 5 on that side, which would be incorrect, right? We'd be going backwards. So what you need to do for the plots for the stem and leaf that are on that left side there, you need to rotate it 90 degrees to the right and then flip it around. Okay, so I know that seems kind of confusing. Mirror image it a little bit, right? If I go like this, right? So if I rotate that 90 degrees down, it looks kind of like that. And then if I flip it this way, my slightly higher peak is on that side and it ends up like that. Right? That's what you have to do kind of mentally with those numbers there that are on the left side there. So the female distribution also looks to be skewed to the right, but a little bit less skewed than the males. There's that comparison part there. In my spread, the female is going to vary. Females seem to vary more. So it seems to have more variation with our actual numbers here. So from 13 to 57, where males have less variation. So there's our comparison language, 4 to 35. Okay, so hopefully if you took AP Biology, you remember how to make a histogram. Remember, a histogram is showing you how often particular data shows up. So a histogram is always going to have frequency or relative frequency or percent on the y-axis. On the bottom, on the x-axis, it's going to have my particular, data points that I have there. So in this case, on my x-axis, I'm going to have percent of foreign-born citizens, or I don't know, people that are living there, residents. Okay, so my percent of the state's residents that were foreign-born. And then remember the histogram. A histogram is done, let's just do the frequency one. So let's see, my highest one is 20. So, okay, so I've got 4, 8, 12, 16, 20, 24. That's high enough. Okay, and I'm going to do frequency. I need my units over there. This is getting beyond messy. There, frequency 24. Okay, so remember histograms are divided into bins. So if you look here, they gave classes. So 0 to less than 5%, 5 to less than 10%. So these would be my bins down here. So I'd have 0, 5%, 10%, 15. So my bins are going to go by 5s. And so, for instance, where it says 0 to 5, less than 5%, so this is 0 to 4.9999999999999. A 5% or higher would go in this bin to the right. So, for instance, I have 20 states that have 0 to less than 5% of their residents are foreign-born. So, 4, 8, 12, 16, 20. So, this bar would go to here. If I dot plotted this, right? I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You get my drift, right? I'd go all the way up to 20 in this bin. So that's my first bin there. Okay, my second bin, 5 to less than 10%, has 13. So again, I go up to 13. So there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 data points that fall in that range of values. So for instance, Alabama would fall in the first bin. Alaska would fall in the second bin. Okay, I can't tell by looking at this histogram that Alabama is 2.8%. All I can tell is that there are 20 states that have less than 5%. Okay, my third bin is 10 to less than 15%, which is 9 states. So, oops, man, I'm having trouble drawing straight lines. So again, 9 states. You don't have to draw the dots. I'm just trying to kind of help you visualize what's happening here. 5, 6, 7, 8. 9 states fall there. In the 15 to less than 20, I've got 5 states. So 1, 2, 3, 4, 5. In the less than 25, 20 to less than 25, I have 2 states, 1, 2. And in the 25 to less than 30, I have 1 state. So this is what a histogram looks like. It looks kind of like a bar graph, right? But it's telling me how often I'm going to see data points in a certain range of values. So it's not giving me specific data points. I can't pull specific data points off that graph. This is really helpful for really large data sets. It allows you to see patterns and trends so you can start kind of analyzing that data. So this is just a little bit of a cleaner version of what I was showing you before. So here's our percentage of foreign-born residents. You can see our bin sizes here, 5, 10, 15. Remember the bin here, like if I had a value of actually 5%, it usually goes to the bin to the right. 10% would go right here. So like for instance, the one of these dots right here is probably a 2.8%, that Alabama one that we were talking about. So there are 20 states that fall in this range of 0 to less than 5%. When I stack them all on top of each other, I get 20 high. So I have a bar that is 20 high for my number of states. Now, when I look at the histogram again, I can't pull that specific information of a particular state or even what one particular data point has. So when we're analyzing histograms, we have to realize it could be, I could have all 20 of these dots could be 0. All 20, this one dot here could be 29.9999 forever. Or all 20 of these dots could be like 4.999, and this one could be 25. Like, we have to understand that when we're looking at center and that kind of thing, going to have to give possible values, not say, oh, it's exactly this, because you can't read that from a histogram. You can only say things like the midpoint is going to be between this value and this value. So let's take a look at this final question here. So about 1.6 million first-year students enroll in colleges and universities each year. What do they plan to study? The graph on the next page displays on the percents of first-year students who plan to major in several discipline areas. So the first question here is asking us, is this a bar graph or is it a histogram? So, and we have to explain why. So when we look at this data, yes, it tells me percent of students who plan to major, but these are not measurements on the bottom. These are categories. I am sorting data into these categories. Okay? So this is a bar graph. Okay? I can easily see, oh, okay, there are 18% of them are going to be business majors, professional, other, arts and humanities. So this is a bar graph, field of study being categorical. The second question here, would it be correct to describe this distribution as right skewed? Why or why not? Okay, so no, we would not describe this as right skewed because categories can be listed in any order. They just happen to look like they're kind of sloping down here, but categories don't have to be in numerical order or anything like that because they weren't measured. They're not quantitative. So we could rearrange these categories into whatever order we want, and it could end up looking like, like this, and nobody can do anything about it, right? So no, we would not describe this as right skewed. All right, so like always, we'll do lots of practice with this stuff in class, and we'll go from there.